This is my great pleasure to introduce Professor XiaoFeng Wang from Indiana University, who is the chair of ACM, Special Interest Group on Security, Audit, and Control. XiaoFeng is well known in his research in system security and data privacy. You can see from his bio that he has made outstanding contributions in this research field. For this seminar, he has a very interesting title, Confidential Computing, Challenges Today and Opportunities Tomorrow, obviously, which has a broad scope. I'm looking forward to finding out what he will say, and I'm now giving the floor to XiaoFeng.
Thank you, Liquan, for the introduction. I'm very happy to have this chance to share with you guys our research in confidential computing in the past few years. But before that, I would like to tell you a story. A student of mine back a few years ago complained to me that security is too hard. And if you're working in this area, you have to spend months of effort to think about a research topic, come up with solution, and a painstaking effort to build a system, experiment, and do whatever analysis you could. Then write a paper and waiting for the unpredictable result. And the length of a project and typically will be one student 6 months. But looking at other areas, particularly artificial intelligence, machine learning, and if you have an idea and you write a few proof and you adjust some parameters, you can quickly publish a paper. And he thought it's so unfair. So what I told him is, yes, right now it looks like security is a harder path, but you shouldn't just look at what happened today. You should look at what's going to happen tomorrow. Guess what? Back 17 years ago, when I was a student at Carnegie Mellon, half of my dissertation is on machine learning AI. I published a paper, at triple AI at NIPS in 2002, 2003. But when I graduated in 2004, I cannot find a job using my AI credential. So that's the end of AI winter. It's pretty much like you have a good AI publication, but which does not guarantee you can find a faculty position. The reason I can still find an academia job is because the other half of my dissertation is on security. During my career, I have witnessed ups and downs of many areas, but no matter which area become popular, there are always security privacy challenges. There are always security and privacy opportunities. So that's good things for security and privacy research. Hope what I said will make students in the audience working on security a little bit more comfortable. But during those years, I've been also asking myself, so what happened to the AI? So what happened that has brought AI out of the woods? What happened has made AI great again? So my personal opinion is there are two important things. The first is advancement of the hardware technology. Today, we can afford to train a very deep neural network that we couldn't back decades ago. The other important thing is availability of big data. Only from those massive amount of data will we be able to extract deep knowledge. So looking down the road, are we looking for, will there be another AI winter? So it's pretty much depend on whether we are going to have more data or less data. So this is looks like the answer to this question looks like quite obvious, right? And just look at what happened during this 1.5 years. We have to communicate through internet. We have to teach through internet. We have to attending conferences through internet. So we generate a huge amount of data. If you look around, we have a smartphone, we have the smart device everywhere, which aggressively collect our personal information. A lot of data, a huge amount of data are being generated. How come we could have less data down the road? But just because a lot of data has been produced does not necessarily mean more data will be available for AI research and development. Why? Because there's a huge hurdle. The hurdle is privacy. And in the back 7 years, I'm sorry, the slides are a little bit out of date. And we have a witness, just these all kinds of data breaches on yearly basis. You have a Home Depot data hacked. And for the Equifax data breach in US, it's affect almost half of the population of the country. And the Facebook data leak might potentially affect presidential election. So in the present of huge amount of data breach, country around the world and come up with all kinds of legal and policy regulations and trying to limit data sharing. For example, in European Union, there's GDPR. In US, there is a California Consumer Act. And under those law and the regulation, sharing become no longer free. So for the researcher, oftentimes we are stuck in the rock and hard place. And we want to share data, and the data is the lifeline. Data is the fuel for AI engine. And in the meantime, and we no longer can we share it freely because those legal and policy restriction, because our responsibility to make sure and that the privacy of individual has been well protected. So how to solve this dilemma? And as a security researcher for decades, we are studying a magic technique. What we want to do is we want to still allow people to freely share the data and use the data and to extract their value, but without seeing their content. So this technique called confidential computing is essentially want to use the data without seeing its content. And for decades, and people studied crypto solution. For example, homomorphic encryption, which allow any function to be computed on encrypted data. And the secure multi-party computing, and we can allow multiple parties to jointly compute a function without exposing their individual data to the other party. Those techniques, and they are theoretic sound, and they are step close, they are moving forward quickly. But unfortunately, so far, they are still distance away from practice in terms of performance. For example, for fully homomorphic encryption, it's still orders of magnitude slower than we hope. For secure multi-party computing, yes, today if we have 3 machines, for example, attached to each other with high speed collection, and then you can do secret sharing, and there are techniques which allow you to train a deep neural network. But the problem is, if indeed we want to distribute the trust across different parties, for example, and sharing the secret across Amazon, Google, and Microsoft Azure, and you want to cross internet to train a deep neural network, use secret sharing, within a reasonable amount of time, I think the technique is still not there. Alternative solution is hardware support trusted execution environment. An example including Intel's software guard extension and SGX, and more recently, their proposal of trusted domain extension, and AMD's memory encryption technique, SEV, and ARM's TrustZone, and their vision about confidential computer architecture. And also there are some other approach published in papers, and for example, Keystone, Enclave, Graviton, and High-T, which I'm going to talk about today. A prominent example is Intel's SGX. it is a trust computing, and it's a trust computing systems which built into Intel's SGX. I'm sorry, built into Intel CPU. And so you're going to trust the CPU. And when you run this trust CPU, it will create a trust execution environment and using a protected memory. So that memory region is called enclave. Data outside the enclave are fully encrypted, which cannot be decrypted even by the privileged software, just like operating system. And before read the data into the enclave and decrypt the data and running exposed to the program, the enclave will first running a remote attestation to prove to the owner of the data that only trusted program will be executed on the data. And in this way, not only we can defend against the threat from privileged operating system, but we can also provide some protection against even physical attacks, such as an untrusted system administrator. So this type of trust execution environment has been studied for a decade. Security researchers looking from the different aspect of this new generation TE and trying to understand their effectiveness, the protection they can offer. And from defender perspective, we want to protect data, we want to protect computing. And the attacker, they want to steal the data, they want to compromise the integrity of computation. And for this purpose, the adversary trying to explore some weakness inside the system. There are some weakness which can cause direct damage, for example, data exposure and the integrity compromise. But those problems are exactly those trust execution environment are designed to defend against. But there's a subtle issue, and which called sidechannel. This problem originally was outside the threat model of those TE design. For example, SGX has explicitly mentioned at the very beginning that they don't consider those sidechannel threat. So sidechannel is essentially a kind of side effect when the protect program running inside the enclave, processing those sensitive data and generate. And those side effects could be observed by the adversary outside the enclave and used by the adversary to infer the execution inside the enclave and even to infer the content of data. For example, and the original design SGX 1.0 and the page table of those pages inside enclave has been exposed to the operating system. Although the OS cannot see the content of the page, but they can manipulate the properties, the features on page table entry. For example, they can turn off the present bit on the PTE. So when the process running inside the enclave touch a specific page, it will trigger a page fault. And the page fault will cause a synchronized enclave exit, AEX. So this will be observable to the malicious operating system. So the attacker looking at the occurrence of AEX, they can figure out a sequence of page access. And those page access could be tied to the value of data. As you could imagine, if there's secret bit wins 0, and the program will go down one path. If it's 1, it's go down different paths. Each path will generate a unique sequence of page access. Then observing those page access, the malicious operating system will be able to figure out the value of that secret bit. And there are some other side effects which operating system and system level adversary can take advantage of. For example, and the cache, cache side channel and other microarchitecture level side channel and weakness they can take advantage of. For example, and the speculative execution, which those attacker can use to exfiltrate the data into the cache. So you can use cache-based side channel to infer the content of data. And also inside this environment, the adversary has high privilege, and they can they can manipulate the computing environment and to take action, trigger the side channel event. For example, set off those present bit on the page table entry. They could also, make the environment very silent so they can amplify the signal for those side channel. So right now, a well-recognized problems and a major challenge to the privacy guarantee and for the trust execution environment is how to reduce side channel attack surface. I think all the previous research people think about is more like this whack-a-mole solution. And whenever you find a problem pop up, you're trying to hit it in the head. You're trying to just address this exact problem. And people are using this mentality to deal with those side channel leak. And I'm going to say it's a bad idea because side channel is not a problem. It's a set of problem. And we are continuously discovering new side channel. If you're just trying to solve one specific side channel, it's just like you do optimization and you only care about the local optimality, right? But if you're looking at I think a better solution is looking at the whole spectrum of side channel attack surface. We are trying to reduce the old side channel attack surface, not just a single one. So in this way, we can do a global optimization to minimize the risk we have been exposed to. But the question is how are we going to do that? So an idea we had a few years ago is how about we are trying to find some overarching condition for all kinds of side channel attack on TE. If we can remove those conditions, those necessary conditions, maybe we can completely shut down the surface, all the side channel attack surface on TE. Right? It's a kind of ambitious, but even if we couldn't do that, and if we can find out some condition behind, a set of side channel, remove that condition can also significantly raise the bar for side channel attack. So back a few years ago, and my collaborator and I, we took a look at the different attack surface in a computing infrastructure. And what we found is very, very interesting. Yes, there's a lot of side channel attack opportunity, but from the attack's perspective, and it's not that easy to successfully attack a system, but in the meantime, keep the attack stealthy. For example, for the page fault attack, the attacker used to induce page fault. It can be observed and by the malicious operating system, but in the meantime, it can also be observed by the thread running inside the enclave. So if the attack is no longer stealthy, the defender can take advantage of those observations to put a protection in place. An example is SGX, and which you use transactional memory and to perceive those interruptions and then take protective measure. So a question is, how can we, from the attack perspective, how can we, launch a side channel attack, also make it stealthy? So one solution is take advantage of hyperthreading. So the good things for hyperthreading from the attack's perspective is it allows two threads running side by side in one CPU core. So, and their context switch will not trigger any interrupt. If we take a close look at those attack surface, what we found is, and some attack can only succeed and with the help of hyperthreading. For example, if you want to use store buffer, you want to use a floor point unit or translation local side buffer. Well, some other attack, for example, cache-based attack and using branch prediction unit, and you don't need to rely on hyperthreading. But if you don't use hyperthreading, then you will continuously trigger interrupt, which become observable to the thread running inside the enclave. So attack is no longer stealthy. So the key here is hyperthreading. If we can control the hyperthreading surface, right, and then we can at least make those not a single one, but a set of side channel attack no longer stealthy, and we can significantly raise the bar to this type of attack. So what is hyperthreading? Hyperthreading is a proprietary implementation, Intel's proprietary implementation of simultaneous multi-threading. So the idea is very simple. In the older CPU, and each CPU can only handle one string of execution. But in a modern CPU, and you can run 2 threads. The reason is, and those CPUs are designed to have 2 sets of registers, and you can keep 2 threads and context inside this inside the CPU core. And but still, and these 2 threads, they are sharing some resource. For example, they share the same set of L1 cache. They share the same branch prediction unit. They share the same translation local side buffer. And those shared interface and allow a malicious thread running inside the CPU core to observe the activities that has been performed by a protected thread, for example, a thread running inside the enclave. And this constitutes a side channel attack surface. So the simplest way is we can turn off hyperthreading, and which allowed on Intel CPU. But problem is we will significantly degrade the performance, which we don't want, because as I mentioned, whenever we talk about trust execution environment, the 2 things we care about is security and performance, right? So we don't want to sacrifice our own performance. So how are we going to do this? So our solution, our research was trying to find a way to control this hyperthreading surface without undermining the performance of the system. So our idea at high level is very simple. And we are thinking about inside the enclave, we run 2 threads. One is protect thread, the other is called a shadow thread. Both threads will do useful job, so we can make full use of the CPU core. But we are trying to arrange both threads on the same physical core. So if we could do that, then we fully occupy that core. We prevent the attack thread from getting to the core and from peeking into the operation inside the protected thread. But this is not easy, because as you could imagine, the operating system is untrusted. The OS at any time can separate these 2 threads. So to defend against this attack, our solution is we're using a collocation test. So both threads run the collocation test at the beginning of the execution to ensure that they are indeed running on the same physical core. And during the execution, if the operating system trying to separate them, then inevitably it will trigger AEX. So during the runtime, they will continuously monitor the occurrence of AEX. If there's one AEX observed, that means the OS already moved one thread to a different CPU core. So at that point of time, they have to run the collocation test again. If this time collocation test fail, then they will terminate, because and they believe something wrong happened. The operating system has separated them, and the OS may inject a malicious thread into their CPU core. So the key here is how we're going to design this collocation test. Make it simple, effective, also reliable. So we come up with a very smart idea, and we are trying to use a contrived data race to perform this collocation test. Race condition is a bad thing. Race condition is a bad thing for parallel computing, right? But in our research, we turn it into a very good thing. And we turn it into protection against a side channel attack. So the idea is very simple. We have a variable. The variable is inside the enclave, is protected. That is the operating system from outside cannot change its value. Right? But and the 2 enclave threads can touch that variable, and they concurrently write and read to that variable. To make it simple, and let's consider a situation that the protected thread continuously writes 0 to the variable and wait for 10 circles and read it out. while the shadow thread continuously write 1 to the variable. So if both threads are running on the same CPU core, they will communicate through L1 cache. This is very fast as execution, as a single instruction. So if that's the case, as you could imagine, because one thread continuously write 1 to the variable, while the other thread write 0 and wait for 10 circle and read it out. So the protect thread is most very likely, find out the value of the variable is 1, right? Because the shadow thread continuously write 1 to that variable. But if operating system trying to separate these two threads and onto two different physical core, we continuously play this game, right? And the shadow thread keep on writing 1 to the variable, while the protect thread and write 0 and also read it out. So the communication no longer can happen through L1 cache. In order to synchronize their cache, we have to run this cache coherence protocol, which take a long time. On the Skylake architecture, is 190 circles. So that means, and for the shadow thread, if you write 1 to the variable, you have to wait 190 circles until the value has been synchronized to the L1 cache of the protect thread. So as could imagine, for protect thread, you write 0 to the variable and read it out after 10 circles. So most likely you will get 0 and not 1. Right? So using this trick, and we can immediately find out whether both threads are running on the same core or different core. And in our real design is a little bit more complicated, right? And both threads are continuously write 0 and continuously write a value to the variable and continuously read it out. And also we are not just putting 0 and 1 there, and we're putting a sequence of numbers so that those threads can figure out their synchronization stage. But the high level idea is the same. And if both threads running on the same CPU core, the communication time is short. So, and whenever you read the content out from the variable, most likely you will with at least half chance you will figure out you will find the content written by the other party. But if both threads are running to just a different CPU core, then the communication time is much longer than the execution time. So for each thread, if the thread read out from the variable, most likely it will find out the content itself put into the variable. Right? So in this way, using a hypothesis test, we can differentiate between these two worlds and whether they are running on the same core and two different core. So by doing so, we can find out if operating system has stealthily separated both threads, at that point of time, that means the enclave exposed to a side channel attack, so they can terminate its execution. In our research, we have built a compiler using LLVM to instrument enclave code, and with synchronization, with collocation test, and both code are supposed to continuously check AEX, because AEX could be an indicator that operating system trying to separate those threads. And once an AEX is discovered, you have to run the collocation test again. So as you could imagine, the performance of the system, it depends on the frequency of AEX, right? So in our research, and we analyzed our system using micro benchmark, what we discovered, even when AEX happened at a very high frequency, for example, 1,000 times per second, still, and we can achieve a relatively high performance. The overhead introduced is only 16.6%. So here I just give an example. Our solution is by no means perfect, but we demonstrate this mentality and trying to find overarching condition to shut down all the attack surface is feasible. And the condition we discovered and allow us to raise the bar for a set of side channel attack. It's incomplete. I believe there are some other overarching condition inside the system. And if you find it out, and at that point of time, and we will be completely shut down the attack surface. So another important lesson we learned here is, for side channel research, we shouldn't just looking at individual problem, and we should do global optimization find out a solution to address not a single problem, but the whole spectrum of attack surface. So another challenge we face for the trust execution environment is how to enable accelerated confidential computing. Just as I mentioned, and when it comes to confidential computing, we're always asking two questions. Is it secure? Will it scale? Right? The scalability is a huge issue, particularly for artificial intelligence. As you could imagine, those for AI computing today, we are going to use GPU, we are going to use TPU, we are going to use all kinds of accelerator, right? And but unfortunately, those accelerated computing do not support trust execution environment. We don't have a TE in GPU, in TPU. Of course, and you can say, let's wait for NVIDIA to build the TE into GPU, but it's going to take a long time. You know, any chip level change is going to take a very long time. For example, Intel took about 10 years to build up this SGX protection. Right? So the question we were asking is, can we, using today's technology, and to build a trusted execution environment, and to provide support and for accelerated AI? And our research showed this is feasible. So our idea coming from inspired by today's infrastructure of cloud data center. And those cloud data center, their mentality is they are centralized managed resource. They put the computing resource together, then they allocate the resource on demand based on the computing resource need of different computing tasks. So our question is, can we also centralize, control all these acceleration computing resource in a centralized way? And can we also control the confidential computing resource in a centralized way? Then we allocate the computing resource on demand, right? So in the end, we come up with a design which build up trust execution environment out of box physically, and instead of relying on the TE, which already built into CPU, the TE already built into a server, we think about a separate trust execution environment, a heterogeneous T box we call high T box. So that high T box is mounted on a server rack, and together with a set of servers, they are connected with each other with PCIe resource sharing fabric to enable high-speed connection. And this high T box itself, its cases is tamper resistant. If there's unauthorized access to the box trying to open it, and it will raise alarm, it will also destroy data. So inside the box, and we have a security controller, which is our trust computing base. It controls a key component, which is PCIe switch fabric. So that fabric, just like a hub or router, it connects all kinds of resources together. On one side, it connects all the accelerators and for the servers on the same rack, GPU, TPU, and FPGA, all the accelerator. And also it connects to a set of proxy computing node. Those proxy nodes are weak CPU, a micro CPU, micro server integrated on board. I'm going to show you later. And those servers are used for confidential computing inside this high T box. And we can do this because for modern AI computing, and we don't have a lot of expectation for CPU, and actually we put a lot of faith in GPU. And on the other hand, the PCIe switch fabric connect to the servers outside. All the servers and on the same rack, they provide a high-speed connection and a high-speed, and connection and enable high-speed interaction. And today's PCIe and Express fabric, they are characterized by their software-defined features. So the security controller can dynamically adjust the infrastructure and to enforce it through those and the PCIe fabric. And also it can used to enforce different kind of security policy. For example, if you build an infrastructure to connect a host to an equipment, a GPU, and the server and the GPU can only see what the security controller allows them to see. So using this fabric, and our system can operate in both a secure and insecure mode. In the insecure mode, the security controller in the fabric will dynamically collect GPU, and accelerator to the servers on the same rack. So if the server wants to train a machine learning model with public data, they can use GPU accelerator, and just like those devices are directly attached to them. But if computation involves sensitive data and a medical record and a private financial information, and in this case, the security controller will run the fabric to connect proxy node to a set of GPU to form a physical enclave. That enclave is physical because they are physically separate from other computing unit, proxy node and server node. So inside this physical enclave, and we can perform confidential computing. So specifically, and if once the security controller receive a request for confidential computing, it runs the PCIe fabric to connect a proxy node with a set of GPU to form this enclave, right? And then it runs secure boot and to reboot the proxy node and accelerator into a secure mode, into a trust mode. After that, the secure controller communicate with the data owner using remote attestation to prove to the data owner indeed the state of the enclave is clean, and also do key exchange. So the data owner can encrypt her data and a computing task upload to the security controller. The security controller will decrypt the data and send it into enclave. The execution will only happen inside the enclave. So this execution is completely isolated from other computing unit. So if there's another enclave, the proxy node, they cannot touch each other because the control enforced by PCIe switch fabric. And also it completely isolated from the untrusted server on the same rack. They cannot communicate with each other. They cannot even see each other, right? So we can ensure and the isolation is very strong. And also, and this prevents those direct attacks. Even the side channel attack surface has been minimized because, as you could see, the only thing they can observe with each other is just this interface, is the PCIe interface, is the secure controller interface. And otherwise, they don't have any interaction. So in this way, we can minimize the side channel information exposed to the different enclave. We implement this design into a prototype system, and we use this PAX and 9797 as a PCIe fabric. And also the security controller is built into an x86 CPU board together with FPGA coprocessor. The proxy node is a set of high density microserver. On one board, we can integrate 2 servers. And if we want to, we can integrate 4 servers, right? And so 2 boards, we can have 4 to 8 servers. And the remaining part are GPU, right? And if with extended cases, we can integrate more proxy node, we can extend more server. So we can concurrently have a more physical enclave. So the TCB is thin. What including in the trust computing base is just hardware of FPGA coprocessor, and also firmware, which is the software stack, and for the security controller. For security controller, and that firmware is designed in a way that is very small. It's only 1% of a standard Linux system. And also we have to trust the GPU firmware. But fortunately, today's many modern GPUs, they have a secure boot support. So we can ensure no matter what kind of task it run before, and after secure boot, it will restore to a trusted state. And also we need to trust the microcontrol unit. So that unit is for detection of anomalous unauthorized activity on the box. If we want to cut it open, if you want to shake it, and all these will be detected. So it will raise alarm, and at some point of time, it will command and the unit inside the system to remove the data. If we look at the money we have spent on the device, what we are going to see is, and the most expense are on those shared devices on GPU, which can be shared across the rack and used by all the server on the same rack. Well, the expense for dedicated computing unit for the security controller, proxy node, self-destructing module, and the backplane is very limited. Even use low-end GPU, and the shared resource take about 75.1% with the price a couple of years ago, and with high-end GPU, it's goes up to 96%. So that means most money has not been wasted. And we also design a set of API surface. So through this surface and the interface, and the user could communicate with IT box, and use the API call to do remote attestation, key exchange, upload encrypted data and the computing task, and retrieve the computing result back from the IT box. In our research, and we perform experiment, and we run a really deep neural network, the neural network of a real world scale on millions of images and collect from ImageNet. And we use this VGG16, GoogleNet, and ResNet 152 with 152 layers. And for the inference, as you could see from this image, in the most cases, and particularly for the truly deep neural network, just like VGG16 and ResNet 152, the overhead mostly below 5%. The exception is for GoogleNet. The overhead go above 100%, and this is because GoogleNet, unlike other neural network, is not very deep, and so it's fast. And so at that, and in this case, the overhead introduced by high T will become prominent. But when it comes to training, as you could see here, in all these cases, the overhead are below 4%. Particularly for the truly deep neural network, VG16 and ResNet 152, the overhead in the most cases are kept below 1%. The only exception is VG16, and when the batch size is 64, it goes above a little bit above 1%, below 1%, and 1.5%. So this research and demonstrate, indeed, just even use today's technique, we can build a scalable trust execution environment to provide real world support for accelerated AI computing. And with all these techniques become increasingly mature, we open the door to great opportunities. Among those opportunities, one of the important ones is confidential biomedical computing. Biomedical research is unique in a sense. It involves a huge amount of sensitive private information, and patient's medical record, and DNA trace, which may indicate a certain kind of disease. But in the meantime, it's a research area that desperately needs data, desperately needs free sharing of data. So as you could imagine, in the past 1.5 years, if every country is willing to open their data set, allow other countries to look at the patient data, all kinds of information, then the world would be in a better place, because and we could find out the problem faster, and we could come up with solution quicker, and we could just design a more effective therapy, medicine, vaccine, right? But this couldn't be done because we have personal information, and we have a private data, sensitive data involved. So confidential computing can play a critical role here to extract the value of the data to facilitate biomedical research without undermining the privacy protection. So for this purpose, in the past 7 years, I'm sorry, the slides are a little bit out of date. And we organized this genome privacy competition with NIH. And the purpose is we want to bring the security and privacy researcher and to the biomedical community to understand the challenge, the problem they are facing, to come up with a solution they can use. And the result will be evaluated by the biomedical community. So our competition has been reported by GenoWeb and Nature News. And in the past 7 years, start from 2014, our competition track, including homomorphic encryption, secure multi-party computing, and more recently, trust execution environment, and also blockchain. I want to ensure the accountability. And also, in order to protect the outcome of the data and prevent the attacker using the outcome of computation to infer its input. And we also have this and the differential privacy track. And at the very beginning, the competition was attended by the competitor from 2 countries with 33 registration. In 2019, we have 21 countries, the participants from 21 countries with 105 registration. Even during the pandemic, and we have 115 registration last year, and from 21 countries. So last year's competition, we have 3 tracks. And the first is secure multi-label tumor classification using homomorphic encryption. The second, using SGX and to do privacy preserving clustering of single cell transcriptomic data. And the last one is differentially private federated learning for cancer prediction model. An example I can share with you is our TE track in 2019. So at that time, and we pre-trained a model for predicting the response of cancer treatment. So that model has trained over the real patient data over for 200 breast cancer sample. The model size is 300 megabytes, but we'll challenge the computer to run it inside enclave. For SGX 1.0, and its EPC only have 128 megabytes. And if you have to run all kinds of SDK, then the available size is only less than 100 megabytes. So you have to significantly reduce the size of the enclave while maintaining its performance and accuracy, most importantly. So as you could see, the winner solutions can achieve accuracy over 98%, and but it's still kind of slow, and nearly 1 second, and one inference nearly 1 second. This is because I think partially because today's TE cannot support accelerated AI computing. Well, I just mentioned that using high T, we can enable this computing, and hopefully we make a step closer to practice. And this year's competition, we have these 3 tracks. And the first, again, is blockchain. It's organized by UC San Diego. The second, is we're using homomorphic encryption-based secure viral string classification organized by UT Health. And this is IU, and we organize this confidential federated learning to train a model for determining a very rare heart condition. So the competition is already ongoing. The deadline is next month, August 18. So if you are very ambitious and you want to jump in the middle, and you are still allowed, and you can try. But at the very least, I will be encouraging you guys to participate in our workshop to witness the progress of confidential computing technique in this area. Now it's already 15 minutes. I think it's time for me to wrap up my talk. Right? And there are some big questions in the confidential computing area, but the most important one I'm going to asking is, how are we going to narrow the trust gap between TE and a crypto solution? And if we're using crypto solution, And we still need to trust the hardware to some extent, right? Because you don't want the hardware piece running your crypto algorithm actually has a Trojan, right? So in this case, your crypto key will be stolen. But for the crypto approach, and we will not trust the hardware manufacturer with the root key, right? But unfortunately, that's the case for the TE, for today's hardware TE, for SGX, for SEV. So in the hardware manufacturer will embed the root of trust into the CPU core. So, and I think important things we need to do down the road is we will move this root of trust from the hand of the hardware manufacturer to the hands of user, right? And in this way, we could make TE more trustworthy. The other important issue here is, crypto solution has been proven to be secure, but the proof is kind of, just reduced to hard problem, right? But still, they provide some kind of guarantee, security guarantee. But for trust execution environment, what we need is formal verification, is thorough verification of the design and implementation. If we could do this, and then we can significantly narrow the gap between the TE and the crypto solution in terms of trust. And at that point of time, the performance advantage of TE will stand out. So, and this will enable us to do a wide spectrum of things which we couldn't do today. As you could imagine, we can enjoy all kinds of internet service, and we can enjoy all kinds of personalized service from Google, from those big companies, without worrying that they are collecting our data. They know too much about us, and they are trying to manipulate how we think, right? And we have the freedom of enjoying all the benefit without worrying about our privacy. And that's the future. I believe with the further advancement of TE technique and other confidential computing technique, that day will come in the near future. Thank you. That's all my talk.
Thank you very much, XiaoFeng. Thank you for excellent talk. Yeah, so now we have some time for the questions. I'm looking anybody raising your hands or put your question in the chat box. Either way you can do. Okay, one person already, so Tias.
Hi, XiaoFeng.
Hi, how
good
are you
to see
doing?
you. Good, how are you?
Wow.
Yeah, long time no see. I have a question going back to side channels.
Okay.
So I can see like too many ways to protect against these things. One is maybe at design phase, try to eliminate side channels by basically not sharing anything.
Which is a bad idea.
Which is a bad idea. And the second one, which seems what we tried in the past, but also you seem to hint towards in some of your designs, is focusing more on detection, like focusing more on understanding what are the characteristics of the side channel adversaries, and accept the fact that we're going to have side channels, and basically focus on detecting them. Is that the way that you see this going? Like us focusing mostly on understanding the characteristics of the side channel adversaries and trying to detect them in order to prevent them?
I think, just I support the idea to make the system more side channel resistant and from the design, from the hardware design. But an important thing is we need to strike a balance between the utility and the protection. System is designed for use and not designed for secure. I think I mentioned this back many years ago. If you need absolute security, you don't need to share. You can keep everything into your safe. Then it is secure and absolutely useless. and you need to strike a balance between these two ends. Also, you need to meet the need for different computing tasks. For some computing tasks, you don't need to worry about side channel. Then why do we need to put so many constraints in place, right? So it is very important to find this balance. I think it is a very interesting research direction and on the hardware design. Also, detection is definitely one layer of defense. Side channel defense, just like any defense against cyber attack, and we need defense in depth. We need containment, and we need to predict attacks move and to put protection in place. And we also need detection. It's one layer of defense. And for the hyper risk, the approach I mentioned, it is involves some detection. For example, we detect AEX, then we will run collocation test again. And we also have some containment element because, and what we are trying to do is instead of detect anomalous outside, just like SGX, and we are trying to fully occupy a CPU core and to make sure, just attack will have no chance to inject an attack thread, right? And so it's oftentimes a combination of multiple tasks. But I think the most important directions and the people has been ignored for a long time. So I think it's time to spend a lot of effort on it, is this global optimization approach. Right? Instead of looking at individual side channel, let's look at the side channel as a set of problem, a wide spectrum of problem. Let's try to come up with a solution that optimize across the whole spectrum. Right? And maybe the defense may not be as effective as the design which tuned specifically for page fault, for example, right? But looking at the whole effect, in the end, what you care about is how much information will be leaked out through all the channels. It's not how much information will be leaked out through a specific channel. Right? And I think that this is an important direction to move forward. And also, it's important to think about the balance between this and side channel protection and utility. And with the protection just in place, the ultimate goal, keep in mind, is not to maximize protection. It's maximize our utility of the system. Does this make sense?
Yeah, it makes perfect sense. Thanks, XiaoFeng.
Nice to see you again.
Yeah.
All right, let's see whether there is any other raising hands or the.
Wanted to speak up as well. So. Great talk. Yeah, hey, good to see you. So I kind of wanted to follow up on the same topic, which is, if our goal is to increase the utility, we've seen so much work on side channels. I'd say more work on side channels than usage reports of SGX. And I kind of wonder what you think about this in a fairly high level. We've seen, 5 years worth of work in this phase. Do you feel like it's sort of a major detractor to people using SGX? Because my sense is that there is not quite as much usage as one would like. We have public clouds like Google Cloud and Microsoft Azure often making these things available. I'm not sure how much usage there is, and I'm not sure if there are numbers that show that. I don't know. What are your thoughts on these things?
Oh yeah, and for SGX, and actually, it's a usage and the real world application a little bit disappointing. At least I think it's disappointing compared with Intel's expectation, right? But people are still trying. Yes. I heard about a lot of companies, they're trying to build another layer to enable cloud computing on top of SGX. But also Intel and AMD and ARM, they are also pushing out a different kind of trust computing systems. For example, and Intel has this TDX, and even ARM, and they are go beyond TrustZone. They have this vision about CCA, right? And they have all these things coming out. So one thing I'm pretty sure about is, although SGX may not be the right technique, of course, I still believe there's some potential and to be explored down the road. But even if SGX is not the right solution, but the whole direction of hardware support confidential computing and is still promising. And a lot of people believe that because we cannot just wait on the software solution. Personally, I also agree software solution is an important direction we need to explore. But we do need confidential computing, and we need it, to become true very soon. And given the increasing concern about privacy, given the political atmosphere, as you could see in US, in Europe, and in Asia country, people care about the data, and which become a barrier for the collaboration from and moving science forward. And so confidential computing is definitely an important direction we can move forward. I'm not sure what will be the technique, the most and the popular technique down the road 10 years later. It may not be SGX, but I guess hardware support confidential computing and some kind of hardware support confidential computing could be one of them and become very popular 10 years later. So how do you think?
Yeah, probably true. Yeah, hard to argue with that. That's what happens. But thanks.
Thank you.
Do you have a question?
Yes, excellent talk. Thank you very much. And I have 3 questions actually. Yeah.
Go ahead.
So the first question is about this high T architecture. Do you assume any physical security? Because in the past, like in CPU T, then we assume no one can get into the CPU. But now, if this is a rack, then if some administrator has access to the rack, then they might be able to monitor data transferred through the bus of the motherboard. So
okay,
yeah.
Okay, so I think in terms of physical protection, every solution has a limitation, and even for SGX, you have the root key built into CPU, and there's nothing can prevent anyone to open the CPU and extract the key, right? Of course, if you do this, you destroy the CPU, but it does not matter because you get a key, and you could manage to decrypt the data which are already encrypted, and right, and for the high T blocks. And we can provide some level of protection. We have a tamper-resistant unit if you want to open the box and without authentication and a USB key. So at that point of time, and it will be detected by the sensor, and we are trying to destroy the data. The protection, I agree, is not perfect. And you can have some, sophisticated attack. You can carefully cut it open using laser, and you could use you could boot attack or whatever, or the combination of the element to make it very fast, to open the box very fast, and frozen the memory and trying to extract data. And I'm not saying this is not doable, right? And all what we are doing is trying to raise the bar, make it a little bit harder. And so that is the current solution. What is the current high T, not only for high T solution, but a T solution, all kinds of T solution want to achieve. We don't guarantee absolute secure, and we're just trying to raise the bar for the attack.
Okay, yeah. So my second question is about the genome computation. So from my experience, it's easy to measure the performance of a privacy-preserving algorithm, right? So like the speed, like accuracy, but it's actually quite difficult to measure whether this implementation is correct or it's secure. Yeah, from my experience, I have a cryptography class, and I have a coursework for the students to implement a cryptographic algorithm, and then I measured. I marked the coursework by measuring the time, but I found those coursework that's run very fast is actually not secure because they skip some of the crypto part.
Okay, important step. You don't encrypt.
Yeah, exactly.
Your solution the best. Yes, I agree. This is difficult for our solution and for the competition. And we do have some standard for the security protection. And we will ask the competitor to expand their solution. And in some cases, we will inspect the code. But I agree. Even when we do so, we cannot guarantee that implementation is absolutely correct, and we cannot guarantee someone plays some subtle trick to avoid detection, right? And they can do adversary learning, of course. They could do these type of things, and they can boost up their performance. This indeed happen, and I think this happen for any competition. Right, and you play dirty trick at some point if you don't know, then people can avoid detection.
Yeah. So my third question is about the last conclusion, right? Crypto and the T. So one of the main concern for T is the root of trust, because it's often controlled by one party, like Intel.
Yeah.
And in crypto, we have MPC, multi-party computation. So we can have multiple parties get together to do some computation, right? Can we use these two together, for example, to get the trust roots by multi-party computation?
I don't know, it's possible. It's important direction to explore. And you can have a multiple party and generate the root secret, but and there's gonna be some technique to allow those parties to write those secrets into the CPU core. And you're gonna have some mechanism, right? And for example, suppose you have a automatic mechanism in place which can directly transfer and the secret, the combined secret into the CPU core if they have something in place, and also this device they connect to the internet. Then you have several parties jointly come up with key, each contribute a share, and you put them together with a secret key and automatically return to the CPU core. Then I think it works. But in practice, it could be difficult. There is some alternative solution. For example, you can have a single machine. It's a little bit ugly, but and it might work. You can have a machine, right? And you can first transfer the first party, and then let the first party to write up a root of secret to the CPU core. Then you hand over this device to the second party, and this guy write up another secret key, and to the third party, and this guy written up just their keys. Then in the end, you combine those keys together, so not a single party know the content of key. And I think someone proposed. I'm not sure that there's a paper about this, but at least and just someone even ourselves brainstorm this type of idea, and to see how feasible it is. And theoretically, I think there will be a solution. But if you want to make the solution not only sound theoretically, but also work in practice, and I think this is the challenge.
Okay, thank you.
Okay,
welcome.
We got one person raised the hand. Is the Zoom call, and we got another questions in the chat box. Okay, I probably let the Zoom call talking first.
I have a question on side channels, similar to maybe what Soteris said. I really like the idea that you identified the global problem instead of individual side channel problems. And Soteris was asking also about the detection of side channels. And in order to understand this global prevention, I was gonna ask about the underlying operating system, because in most of the threat models, we say another enclave or another insecure software or the kernel or a malicious operating system is placing the attack. But today we have also secure and formally verified operating system solutions, like for embedded systems, SEL4. Would you be in favor of combining any of the formally verified operating systems as an underlying maybe security monitor or resource manager, and on top of them still utilize the hardware enclaves? Would that be eliminating the side channels also? Of course, it is not a fight against, or it's not a hardening, but it is just trying to, for some set of the applications, it is creating a secure environment. Would that be an option?
Yeah, the interesting things, if we can, for one layer of protection, we can have so much faith in that one layer of protection, the faith of 100%, then we don't need a redundancy, right? and if we believe that layer is always trustworthy, it will never fail us. And so additional protection just introduce computation overhead and will raise the cost for the whole system. So we don't need it at all. But unfortunately, it is that's in the real world, that's not the case. Even the CPU core, even the CPU operating system have been formally verified, and you only verify the presence of some property. And particularly for non-interference, it's very difficult to prove. And oftentimes when you prove it's non-interference, oftentimes, and the system's resource have been so limited, capability has been so limited, and its functionality and will significantly reduced. Right, and we often need to find a balance between the utility and the security. So in this case, if one layer of protection is imperfect, so we have to think of additional layer of protection. We need defense in depth. So we can have a multi-layer of protection, and also this multi-layer of protection can be tuned toward a different computing need. For example, and if you just running a program and which just does not have a lot of security demand, privacy demand, right? You don't need to run into enclave. But and if you run in something highly critical, right? And for some reason, it's involve highly sensitive data, its operation is also very sensitive. Then even if you have some verified CPU core, which may not be perfectly done, and it's better you have another layer of protection and running inside the enclave. With this combination, you can have a higher assurance. So that's my take.
Thank you very much. Thank you very much.
Welcome.
Okay, now we come into the question in chat box.
The chat box is asking my take to implement. What's your? I can show it here actually. And what's your take on to implement your solution to resource-hungry IoT device? And I think for high-T box, is designed for, there are two types of TE. And in my opinion, one is heavy TE, the other is light TE. And the design for high T is for heavy TE, is for accelerated computing, is for cloud computing. The other type of TE is for edge, is for lightweight computing. And so our solution cannot be directly applied for IoT device, but I think it's definitely a good idea to looking into what is the most appropriate protection for those IoT devices on the edge end, and then looking at the lightweight trust execution environment you can design using using RISC-V and build into those systems and demonstrate their work. You can strike balance between the utility and the performance. And this would be very interesting. And also knowing someone is doing the research along this line.
Okay, so Pradeep, are you happy with the answer? Yeah, okay, thanks. So obviously your answer is good. So I have a question, since I haven't seen any other raising hands, so I can probably ask my question then until somebody raise the hands or put the question again. There are a lot of attacks to those 3TE examples you use. Yeah, none of them actually get rid of all those questions, and some people a few years ago and even recently talk about whether SGX is dead or whether the TrustZone need a bigger reconstruction and so on and so forth. And then Trusted Computing Group, the huge industry standard body, they claimed their trusted platform module TPM is in a top the temporal resistant level, because this is a single little chip hardware, and all those SGX or SEV or trust zones, they are claimed by TCG is the integrated or firmware TPM. So what is your comments about those TEs? They may not be high in a high level of a temporal resistant, but still have some kind of temporal resistant. And how about TPM compared with that? Although TPM is not to be able to run your AI program directly, but how about using TPM to build your own temporal resistant software bubble?
I think, and both TPM and the TE, they have a different use, right? And the TPM itself has more temporal resistant features, and which is secure compared with trust execution environment. And they also can do attestation, all kinds of protection. But and compare with TE, and TE designed for not only for security, but also for scalability, right? And the scalability and using a temper-resistant TPM, you cannot perform a large scale computing as we expect, right? And so that's the reason we have to using this trust execution environment. And with those technology, what we hope down the road is, and we can, for example, we can replace today's Facebook, Google, their data collection analyze architecture. They can provide the same service, but in the meantime, even those big corporations, they cannot see our personal data, right? And then we no longer do we need to worry about and they are aggressive collect our information, and we don't even need to worry about data breach, because even the data has been leaked out. The adversary, the attacker, the hacker will have no idea how to decrypt the data because those companies themselves has no idea. So those would be the ideal world. If we can have a design with the highest possible security privacy guarantee, but in the meantime, it is scalable and with high performance, and it can allow us to do all these tasks, and the world would be perfect. But if we cannot get there, we're going to have some trade-off, and we back off a little bit on the privacy protection end, and we're trying to improve the performance, right? And the weakness and can be mitigated using some other non-technical solution, policy solution, right? And other protection in place to strike balance. I guess that's the just the future direction. If we just focusing on the highest possible privacy protection, then unfortunately we could limit the application, the use of trusted computing. And so this may not be a good thing for the whole area. I think we have these different options and different choices. Some is more on the high end of privacy protection, tamper resistant, and even tamper proof, while the other is is lower in security, in privacy protection, but is scalable with this balance, and we can have a more opportunity to use and trust computing and to serve the society.
Yeah, thank you very much. It's still a long way to go. The tamper proof is even
even harder.
Even harder, it's more challenging.
Yeah.